Okay, this is the combined GCSE Combined Science Trilogy Physics Paper 2 Foundation. So figure 1 shows a garden chair. They always like to put diagrams like this. But crucially, it's got a spring on it. Look for the labels chair or whatever, but it's got a spring, so it means we're going to be talking about springs probably in question 1. The weight of the person causes the spring to extend. Why does the weight cause the spring to extend? So we're asking about weight here. What is weight? In which direction does weight act? Does weight act in all directions, upwards or downwards? Well, weight is also to do with gravity or gravitational force, so it's downwards. Complete the sentence. The weight of the person is a, well, I've already answered it, a gravitational force. And again, we're talking about weight, which means it's unsurprising that the next question is using the weight equation. The weight of the person causes an extension of the spring. Okay, so always look for these numbers and what they mean. The extension is 0.07 meters, and the spring constant is 12,000 newtons per meter. So how do we write this? We write W for weight, and it's 12,000 times by 0.070. We do that in our calculator, so that substitution gets us 1 mark. Do it on our calculator, gets us the other mark, which is 840 newtons. You can see they've written the unit for us. The weight of the person. Now, I've added this back in the top because we're still going to need it. So we have the weight, or the extension, and the spring constant. This time, we have calculated the elastic potential energy. So still using the same numbers, but to calculate something else. And so we have E, the little e, is our elastic potential energy. And again, substituting in these values gets us 1 mark. And then our extension is 0.070. That will get us to 1 mark. And then plug those all into a calculator. Will get us our next mark. It's not asked for rounding, and it's only 3 digits, so we can put that in, 3 significant figures. If there's more than one person on the chair, the spring could become inelastically deformed. Now this is the crucial bit here, inelastically deformed. That means you've broken the elastic nature of this spring. So it's not elastic anymore, it doesn't bounce back. Okay, so if we look, we're ticking 1 box. The spring extends more when 2 or more forces act on it. There. The spring will not go back to its original length when the force is removed. Now that is what a spring does. A spring will go back to its original length. So when it's inelastically deformed, or you've broken the springiness, that means it will not go back to its original length. Okay. Then we have the manufacturer of the chair investigated the extension of the spring. We're still talking about springs. And if you look at this diagram, it looks remarkably similar to our required practical about springs. So we have A, well, that length of A is without a spring, or without a weight, I should say. That is our original length. And then if we look at B, this is the difference, because C is with a weight. So if we do C take away A, that's going to equal B, which is that difference. And then when it says which length represents the extension, well, the difference for the extension is the same thing. So that's going to be B. Which graph shows that the extension of the spring is directly proportional. Again, we're looking for these words in our question. Directly proportional means it's got to go from the origin, from 0, 0. Now, if we look at that bit of our definition first, that means it cannot be A, because that doesn't go from the origin, and it cannot be D, because that does not go from the origin. And then directly proportional also means it has to be a straight line. So it has to be B. It's the only other option. Then we have our last one as part of this, suggest 2 improvements. Now, improvements to our investigation. We should always be looking at, is there a method? Have we got a method? No, we don't. Okay, so something we could automatically improve is we can repeat and calculate a mean. That should be our go-to answer. It's only going to be one because you have to do both to improve the accuracy. Repeating it doesn't improve the accuracy until you've calculated a mean and remove those anomalies. What else can you do? Well, this table is quite small. The results table is quite small. We've only got 2 different forces used. So what we could do, which would definitely help us, our results, is use a greater range of forces. We're only using 2 forces. If we used 4 more, or even 2 more, that would be an improvement to our method. Okay, which feature of figure 3 shows that the car travels at a constant speed? Now again, we're looking for words like constant speed for the first 4 seconds. Now, so we're looking at this very first bit until the brakes are applied. Is that line horizontal? No, it could not be that one. Does it go through the origin? It does go through the origin. But does the origin show that it's at constant speed? No, that must be the line going straight. And again, so that's where it's tricky, because two of those boxes are correct, but they're not correct for the question that they've asked, which is about constant speed. The next one, after 4 seconds, the driver applied the brakes and the car slowed down, determining the braking distance. Now, this is what's really important, is you need to be able to read off a graph that first bit, that distance when the brakes were applied was 64 meters, and when the car stopped, that is when it becomes horizontal, and that is at 84 meters. Okay, now the distance the car traveled after the brakes were applied is called the braking distance. So we need to do 84 take away 64, which equals 20 meters. Now, as the car decelerates, we have another equation to use, and it says calculate the deceleration. Okay, now deceleration is the same thing as acceleration, which means we can use that same equation, and instead of writing D for deceleration, it's actually an A, and the change, it actually tells us the velocity changes by 16, and it tells us the car decelerates for 2.5 seconds. So we're going to do 16 divided by 2.5, which equals 6.4 meters per second. Again, it's only 2 marks because we substitute in the numbers, then we use a calculator to get the answer. Now, this black box records large decelerations. It identifies that the driver may be dangerous. Why can large decelerations be dangerous? Well, if your decelerator is slowing down really, really fast, okay, we'll go through. Again, we need to tick 2 boxes. It's saying that. So if we're braking really fast, can the brakes overheat? Well, yeah, absolutely they can. And if you're braking too fast or really, really fast, can the driver lose control of the car? Absolutely, yes, he can. So we think it's those 2, and we'll just check. If you're braking really fast, is the force applied very small? No. If you're braking fast, does that mean the reaction of the time of the driver increases? No, because that's not about how fast you're braking or how hard you're braking. And the last one, the thinking distance. Well, thinking distance isn't about the large deceleration. It's just about how long you are traveling while you're thinking about decelerating. So it has to be those top 2. Then the black box monitors the speed. Describe how speed affects braking distance? Well, it's a relatively straightforward one. The greater the speed, so the faster you're going, the greater the braking distance. The further you will travel while you're braking. If you're traveling 70 miles an hour, you're going to travel further when you're braking than if you're traveling 10 miles an hour. Okay, question 3. Why are the iron filings attracted to the bar magnet? Well, iron is a metal, so again, that's not wrong. Iron is charged. It doesn't have to be. Iron is heavy. Again, that's right. But what are we looking for? We're looking about magnetism. So iron is magnetic. Rather than necessarily the other ones, which aren't wrong, they're just not the right answer for this question. Draw magnetic field lines to show the magnetic field pattern. This is all about, and again, we're looking at 2 marks because it says you should add arrows, which means you can do all these lines to say, yep, I absolutely know what the magnetic field line should look like, but if you don't add the arrows, you're going to lose the marks. So we have to make sure the arrows show that the magnetic field lines are going from north to south, they're going into our south, they're going out of our north for those 2 marks. Okay, you need to show they're going in every direction, essentially, from above it, below it, coming out of north, going into south pole. Figure 6 shows two bar magnets, and the magnets attract. Okay, so we're looking for these words. Attract means they're going together. Now, why do two different bar magnets go together? Well, that's because they are opposite poles. Again, if they're both north, they repel. If they're both south, they repel. It's only opposite poles that attract. Okay, why do the plotting compasses all point in the same direction? If we look at our figure 7, they're all pointing in that direction. And that is because compasses, without a current flowing in that wire, they all align or all point north. They align with the magnetic field of the Earth, which is north. Now, what shape are the magnetic field lines around the wire? It's important we look. There is a magnetic field, there is a current. If we have a wire, what shape will these magnetic field lines be? Well, similar to our magnet, they're going to be circular. We're not going to have triangular field lines or square field lines. We're going to have these circular field lines. And the diagram, it looks similar to one of our required practicals using a spring. Very similar, but this time we've got an electromagnet as well. And it says the current in the electromagnet was the same. Now, as soon as we're looking at this, we're looking at the variables in this box. I think don't mess in class. The dependent is what we're measuring. Well, it cannot be that because they've said it's the same. The independent we change. It cannot be that because it says it is the same. So it has to be our control variable. Now, what is the size of the downward force? We have to look at our figure 8. Again, they're telling us to look in figure 8 because it's in bold. That, if we read it off of the diagram, is going to be 3.6 newtons. And this next question, the distance between the paperclip and the electromagnet is increased. Well, what is increased? The distance. So if we are increasing this distance, the magnetic field will be weaker as you go away from the electromagnet. Therefore, the force will decrease. That attraction, that attractive force will decrease. Okay, now we've got our question about sound waves or longitudinal waves. We can see a sound wave, it shows it in figure 9, and it's asking us to label it. Well, this is a straightforward sound wave, longitudinal wave and sound wave. It cannot be resistance, it cannot be extension. They're about totally different topics. Okay, at least reflection is a vague topic that's similar. Now, one of the words seems obvious. Compression is where things are pushed closer together, and that has to be compression. Okay, so we know we've got compression done. Now, reflection is where something is changing direction, so it cannot be reflection either. It has to be rarefaction. So we can do it where you should absolutely know those words anyway, but also it can't be any of the other ones anyway. Now, which of the following is true for longitudinal waves? I would say in some ways this is for either waves, transverse or longitudinal waves, because all waves transfer energy. That is the crucial bit to remember about waves transferring energy. Okay, then we have this beautiful diagram to scare away birds. But this is the crucial bit because it says both waves are drawn to the same scale. That means you could actually get your ruler out to measure it. Okay. Now, when we look at waves, the only things we care about with waves, or most of the things we care about, are the wavelength and the amplitude. So if we measured the wavelength and amplitude on both of these, because they're on the same scale, we could compare them. Okay. Then it says which of the property changes. So we're looking for one thing that changes. Is it the wavelength? Well, if we look, the wavelength is pretty much the same, but if we look, the amplitude is significantly different. So it's going to be amplitude. Now, figure 12 shows how the speed of sound emitted. Okay, if they use a graph, they will tell you to use that graph, and they've got that question right underneath. So the farmer tests the device on a day when the temperature is 15 degrees. What is the speed of sound emitted by the device when the temperature is 15? So we're going to get to our 15. The ruler we're going to draw up, and we're going to draw across, and that speed of sound is 340 meters per second. Now, for this question, if you notice, it says use your answer to question 4.4. We've got that. That was our speed equals 340, okay? What that means, though, is even if you get that wrong, you can still use the speed from the previous question. So you've still got to use that. So it's worth off choosing a number and answering 4.4, okay? So our distance, well, how far is our distance? We don't know that. That's the whole point. So again, it's 2 marks, so we're just going to substitute in our numbers 340 times by 0.20 seconds, and that is going to equal 68 meters. You get 1 mark for plugging it, substituting the values, and 1 mark for using your calculator. Explain how the time taken for the sound to reach the farmer is affected by the temperature of the air. Now, because it says use figure 14 means we're going to use that. Now, for an explain question that involves a graph, we need to describe the graph first. So our simple description is as the temperature increases, the speed also increases. That's our description. Now, it says explain, which means you need to say why. Well, actually, as temperature and speed aren't necessarily, because we're supposed to explain how the time taken changes. So what we need to say is, as the temperature increases, the speed increases, and therefore the time taken is less. Because if it's going faster, it means it's going to take less time to travel somewhere. Okay? We then have a lovely engineer climbing a ladder. The distance between each rung is 30 centimeters. What is 30 centimeters in meters? Well, we need to know to convert from centimeters to meters, we're going to divide by 100, and that equals 0.30. And then we have again, we have use your answer. So we need to make sure we know that and look back. We know it's 0.30 meters, and it says calculate. Again, it's only 2 marks, so it's only plugging in some numbers. So we're going to do work done equals force they've given us 710, and we're going to do times by 0.30, and that is going to equal the work done is 213 Newton meters. But this next question, the engineer climbs the ladder carrying some equipment. Give the reason why carrying equipment increases the work done by the engineer. Well, work done, if you look up here, is only got to do with 2 things. It's got to do with the force or the distance. So why does carrying extra equipment increase the work done? Well, is he going any further? No, he's not. So we need to say that the force is greater, or there's an increase in force, because that equation tells us that the only 2 things that matter for work done are force and distance. He's traveling the same distance, so therefore the force must be different. The engineer is stationary. Again, we're looking for all these different words in our questions. Stationary means not moving. Okay, which energy stores of the engineer increase? Again, we're looking for something going up due to the engineer climbing the ladder. Right, well, he's climbing the ladder, he's at the top. What has increased? Well, it's not going to be kinetic because he's stationary. Okay, it's not going to be elastic. He's not suddenly stretched his way to the top. And the chemical energy store has changed, but it's not increased. He's not eating food on the way up. So it has to be gravitational because he's higher up, because again, he's top of the ladder, and it's thermal because there's always a little bit of thermal energy store dissipated along the way. Okay, we then have use your physics equation sheet for this wonderful one. Okay, write down the equation that links gravitational field strength, mass and weight. Remember, they always do that alphabetically. So we're going to do weight equals mass times gravitational field strength. Okay, that's our simple equation. And then we have 4 marks. Lots of steps to this equation. We've just been given, or we've written down the equation, so we're not going to get a mark for writing it down. But 2 significant figures is going to give us 1 mark, which means we have 3 marks to use our equation. So there's going to be substitution in, and there's going to be some rearranging to solve for something else. That sort of gives us that hint along the way. Okay. Now, do we have the weight? Yes, we do. So we need to do 710 equals. Now, it says calculate the mass, which means we don't have the mass. So straight away, just substituting the numbers, that gets us 1 mark. We're then going to do 710 divided by 9.8 m, or mass. That gets us a 2nd mark. We're then going to do mass equals, and again, put it into our calculator. This is lots of numbers, 72.4. Again, that's our third mark, but we need two significant figures, so it's going to be 72 kilograms. Okay, the sun emits a continuous spectrum of electromagnetic waves. We've got this spectrum in front of us, we should know. Name the groups A, B, C. It is one of those you just have to know. So we have radio waves in the first, then we have microwaves. You can almost sing this song along. And ultraviolet, then X-rays, gamma rays. So if you don't know that song and you don't know this, learn that song. Give one similarity between the properties of ultraviolet waves and gamma rays. Well, they're all part of the electromagnetic spectrum, so the similarity is they all travel at the same speed in a vacuum, but they're also all transverse waves, because every part of an electromagnetic spectrum of light is transverse. Now, some differences we have. Now, again, being specific, ultraviolet has a higher frequency. Ultraviolet and gamma, no, it does not. Say that's a good check. I checked. I was thinking ultraviolet is the highest, but it's not. We have gamma ray. So ultraviolet has a lower frequency and a longer wavelength. Remember, of course, this is a comparison. Really important, the difference. It has to be the ER words, the lower, the longer, to be able to make sure that they're being specific. I've said UV at the beginning to make it even more obvious. Now, light changes direction when it enters a glass prism. This is something you'll have done in year 7, something you'll have done again in year 11, all about splitting light. And this name for when light changes direction is called refraction. Okay, you need to know the colors of the rainbow as well. Right, write down the equation. Again, you can do it in word or symbol. I'm going to do it in symbol. So it's wave speed equals frequency times by wavelength. And then again, underneath it, obviously, you're going to get this equation to link it to. And it's 3 marks that tells you you're going to have to substitute into values and rearrange to solve. So we have wave speed, that's 3.0 times 10 to the 8 equals frequency times 5.0 times 10 to the minus 7 meters. So that's our first mark, and then we're going to rearrange to solve for frequency. Again, the standard form just makes it look a lot more complex than it is. But again, remember your calculator, you can put it straight in as standard form. They are totally okay with that, okay? And if we get this as the answer, again, from an answer point of view, you can write it in standard form. It doesn't tell you to, but it's perfectly acceptable to. And that's 6 times 10 to the 14. Then we have describe a method the student could use. If they're asking you to describe a method, this is a practical you should have done. This is a required practical, okay? It says your answer should include any extra equipment. Right? That's important to know because it means the diagram you've got, the figure 816, doesn't have everything in it. Okay? Now it's this trolley. There are 2 different ways to do it. I'll go through one of the ways. There is another way to do it as well, which is changing the ramp height. I didn't think I would do that one because a lot of the time we talk about the pulley. Okay, so what is step 1? Well, extra equipment straight away. It doesn't have a pulley. So we're going to add a pulley to the edge of the desk because it doesn't have one. We're then going to attach our mass to the end, to one end of the string, and then the other end of a string to the trolley itself. Okay, that's important. That's some of our extra equipment. Okay, now what are we going to do? Well, the whole point of this is for every time we've done it, we've changed the mass on the end of the string, and it pulls the trolley down. Okay, you can change the height, and it would do the same thing. Now, how do we know the force? Well, we're going to leave that to the end. Okay, but what do we do next? Again, there are 2 different ways to do this. This is considerably easier to describe and use. Use light gates to determine speed. Now that's not where light gates end. because they can also calculate the acceleration for us. They do it all for us. Okay, we then don't have to use a stopwatch, measure the distance between the top and the bottom of the runway, any of those things, because light gates will do all of that. The sort of concept of light gates is a computer that will do all that for us. Okay, now that is our first time of doing it. Well, almost. We're then going to calculate the force, because we haven't actually calculated the force. And the question is all about the acceleration and the force. We've talked about a mass. So calculate force, and again we've got an equation sheet at the moment, so it would be weight equals mass times gravity, and that would be our force of weight. And then what are we going to do? Well, always use an equation. Okay, in fact we've used our equation already. They haven't asked us to calculate the mass of anything, so we don't have to use F equals ma, which is what I was thinking of using, because we can calculate the force. So we've just got the force and the acceleration, which is what they need. So what do? We repeat with different masses. Okay, always important to say what you're going to change. We're going to repeat with different masses, and our final step, always, is repeat and calculate the mean. Okay, again, within there we could say remove anomalies as well. Okay, table 2 shows in a set of results for a similar investigation. We have done this, so you should recognize that table a little bit. You've got the force, you've got the acceleration. Now, which of Newton's laws predicts that the acceleration of the trolley is proportional to the resultant force? So, which of Newton's laws talks about acceleration and resultant force? There's only one that talks about both of those, about acceleration especially, and that is his second law. Now it has, again, I've put the table in again. Determine the acceleration of the trolley when the resultant force is 3.6 newtons. It's quite a bit to this question, even though it's only 2 marks. It says use table 2, so I've shown it again. Okay, we're going to use, the way I would do it is using F equals ma. That's going to determine our acceleration, okay? Now we're going to use the values in our question first. So we can say 1.2 equals, now we don't have the mass, so we need to work that out. Mass times 1.6, and then we're going to rearrange to solve for mass. So we're going to do 1.2 divided by 1.6 equals mass. So for this half of our question, the mass is 0.75 kilograms. That's not the answer, because they're looking for acceleration when the resultant force is 3.6. So we're going to have to put it back into our equation to then work out our acceleration. And again, we're going to rearrange to solve for acceleration this time, which is 3.6 divided by 0.75, and that equals an acceleration of 4.8. Now, we'd expect that to be large, because the resultant force is 1.2, and the acceleration is 1.6. Okay, another way for those people who are better at maths is working out, well, the difference between 3.6 and 1.2 is 3. So if we're going to times this side by 3, we know it's directly proportional, so therefore we times this side by 3 as well. That's also going to get us 4.8. That's, in some ways, a more difficult way, because you really have to understand how those link together in the directly proportionality of it, direct proportionality. Now, this question we have, write down the equation. Well, we've just used it actually. Force equals mass times acceleration. 1 mark. The next one is 3 marks, so we know we're going to be putting some numbers in, substituting in the numbers. Again, very similar to the last question we did. We get 1 mark for substituting in the numbers, 1 mark for rearranging to solve for mass, and our answer is 0.35 kilograms.